All right, today we're going to start talking about inverse relationships. Tomorrow we'll get into the functions and then how we can simplify them a little deeper into those. So inverse functions, inverse relationship, what we're going to do today is use tables and graphs and equations to represent these. Then we're going to write these based on our information we have and by the restrictions on the domain and range. First thing I want to talk about is the symbol we use for inverse. The symbol we use for inverse is an f to the negative 1 x power. This is describing what's going on the left side. Do not try to do the math with this thing. Anything that's attached to that f, the way that you see it, is describing. So this is the inverse function. And inverse is meaning the inverse operations, doing the opposite thing. All right, as we take a look at this, we're going to do a couple of things on this. One, it tells us to identify the inverse relationship, and then it asks us, is it a function? Well, let's answer the question about this one. Is it a function? Remember, what uh, justifies something being as a function is if it does not have a repeat of the x values. So if we look at this function that we're given, our x values are negative 1, 0, 1, 2, 3, 4. So we see no repeats of our x values, so therefore this one is a function. Now what we need to know about an inverse of a function, we'll call this one f of x. The symbol we use for inverse functions is f of negative 1, by the way, f of negative 1. And what the function's inverse is, it will always have an inverse table. So if we have an inverse table, our x and our y values are going to be reversed. So where this one had a value at negative 1, 9, the inverse would have a point at 9, negative 1. Where this one had a value of 0, 7, the inverse would have a value at 7, 0. 1, 5 would be 5, 1. 2, 3 will be 3, 2. 3, 1 will be 1, 3. Give ourselves a little more space here. 4, negative 1 would be negative 1, 4. So that's how we find inverse functions. It's always a really good idea to compare tables, and you should have inverse ordered pairs if these are inverse functions. Now let's justify if this is a function. Well, we do not have a repeat of any of our x values, so therefore this inverse is also a function. And what we're going to learn is that when we have a function that is one-to-one, which this one is, we do not have a repeat of the x's or a repeat of the y values. That's when you have a one-to-one function. Okay, as we take a look at this, what it says is let f of x equal 2x plus 1. And then it tells us to write an equation for the inverse of f of x. Well, very simply put, the way we find the inverse, which is f of negative 1 of a function, is we simply exchange the x and the y value, or in this case, the f of x. Now, I had a student a few years back that showed me that they used f, and a lot of people say use y. I really like what they did. So when I'm going to rewrite this equation, I'm going to put the x over here and the 2f plus 1 over there. So the way that we find the inverse to this function is we solve now for f one more time. So what I'll do is I'll subtract 1 from each side, which is x minus 1 equal to 2f. And then in order to get the f by itself, I need to divide by 2. It's very important you use parentheses when you're about to divide, multiply, really anything other than adding or subtracting, you should. So what we end up with is, move this over a little bit here, an inverse function, f of -1, is equal to what we see right here, x minus 1 divided by 2. Okay, now it says graph the function. Well, we can graph the original function really easy. It has a y-intercept of 1, and it has an order, a slope of 2 over 1. So we go over 2, up 1, over 2, up 1. We would go down to left 1, down to left 1, down to left 1. So now that we've done that, what we want to do is identify our ordered pairs. If we have ordered pairs, it's going to be really easy to find the inverse. So we have an ordered pair at 0, 1. We have an ordered pair at 1, 3. We have an ordered pair at 2, 5. We can backtrack here a little bit too. We have an ordered pair at -1, -1. We have an ordered pair at -2, -3. And then lastly, we have an ordered pair at -3, -5. Well, what that means is the inverse function will have the exact table but inversed. So instead of having a point at 0, 1, it's going to have a point at 1, 0, which would be right here. Instead of having a point at 1, 3, it's going to have a point at 1, 3, it's going to have a point at 3, 1, which is right here. Instead of 2, 5, 5, 2. Instead of -1, -1 is the same reverse, so they're going to actually cross each other right there. We'll have one at -3, -2. We will have one at -5, -3, which puts us right there. So this is how we can find inverse functions. These are known as reflected across the origin, which is this diagonal line, but what you'll see is every point is equal distance from that line. That's when you know you have inverse functions. We have no repeats in the x's or the y's, so this is a 1-to-1 function. All right, so as we take a look at this, it says find the inverse function for each of the functions by identifying an appropriate restriction to the domain. Okay, so what we need to do here is simplify this as much as we possibly can. So this ends up factoring down to x plus 4 times x plus 4, because those are the factors of 16 that can equal 8. If we were to graph this, what this would look like is it would go down, touch at -4, and go back up. Hopefully we remember that from when we were doing our multiplicities. So if you choose to graph that way, that is fine. Go for it. So we essentially have x plus 4 squared. So when we look to find the inverse of the function, the way we do that is we switch the x and the f, and then we solve for the f again. Well, the way I get rid of you got to take care of the outermost stuff, by the way. So if there's adding or subtracting on the outside of the parentheses, you take care of that first. Multiplying or dividing, you take care of that next. So we don't have any of those, so the next thing we need to do is to get rid of this square sign. So we do that by square rooting both sides. Once we do that, we have x equal to f plus 4. So in order to get the f by itself, the last thing we do is we subtract 4 from both sides. It's very important that you do not put this underneath of the radical. So I'm going to switch sides on you here. The f is going to go on the left side just because I like it better this way. And then we would have the square root of x minus 4. Don't squeeze that under there. It has to be there before the square root or cube root or whatever we decide to do. It has to be there first. All right, so we've taken care of the inverse. Find the inverse. Done. And then it says find any restrictions on the domain. Remember the things we talked about. When we divide by a variable, or when we have a square root, we need to make sure that that value stays greater than or equal to 0. So our domain for this would be our radicand, which is x, and it needs to stay greater than or equal to 0. So here's what our answer would be. The inverse is this with a domain restriction of x values needing to be greater than or equal to 0. So the last example we'll take a look at here for today is finding the inverse again, identifying the appropriate restrictions on the domain. We currently have none because we can square any number, so we have no problem here. So what I'm going to do is I'm going to switch the x to this side and the f to the other side. Again, we take care of the outermost things first. So the outermost thing we see here is actually a minus 9. We take care of that by adding 9. So on our left side, it's going to be x plus 9 equals f squared. And the way we get rid of a square is with a square root. So when this is all said and done, we're going to have the inverse equal to the square root of x plus 9. I'm going to just rewrite it over here. You don't have to do this. I like having the f of x on the left side. So we have now created a square root. So we need to make sure that that square root stays positive. We cannot take the square root of a negative number, so we need to make sure that x plus 9 stays positive. So that would be any value greater than or equal to 0. So this one we have to do a little bit of math, just a little. So our domain would be all x values greater than or equal to negative 9. So our function, inverse function, is this, and our domain is that. Okay, so we take a look at this. It says let f of x be 2 minus the cube root of x plus 1, and we're asked to sketch this graph. Well, the best way to sketch a graph is normally just to take it to your calculator and develop a table. So when I do this, I get a table that has an ordered pair at negative 2, 3, which is right here. It has an ordered pair at negative 1, 2, which is right here. And then it has an ordered pair at 0, 1. I keep looking down, and there's a final ordered pair at 7, 0. 1, 2, 3, 4, 5, 6. Barely on the screen here. This is a cube root function. So the shape that it takes looks like this. It's going to start bending back because there's actually another ordered pair way off the screen there, but it would be at negative 9, 4. So we're just going to bend this way. So ordered pairs again, negative 9, 4. There was one at negative 2, 3. There was an ordered pair at -1, 2, 0, 1, and 7, 0. Reason why I want this information is because I'm going to be doing the inverse. When I get the inverse, it's much easier to do this with the table. All right, it says verify that the inverse will be a function and write an equation for this. Well, I can look at these values and see that it is a one-to-one function. The way I know this is because it passes the vertical and horizontal line test. There is no repeat of the x's, there is no repeat of the y's. So I know that this function will be the inverse will also be a function because it passes those. Now, as far as writing this, we're going to go ahead and set up our equation, which is 2 minus the cube root of x plus 1. But we are going to reverse the x and the f and then solve for f again, which is what we did yesterday. Again, we start with the outermost stuff. So the outermost thing that we see here is outside of the radical, which is a 2. It is a positive 2, so I remove it by subtracting 2. That negative sign was not attached to the 2, it was attached to the radical, so it's very important that you recognize that. But I do need to get rid of that negative sign. And the way I do that is to either multiply or divide by negative. It doesn't matter because they both essentially do the same thing. Actually makes more sense to multiply in this case. So I'm going to multiply both sides times -1. So we now look like this. I'm going to distribute this in and change this to -x plus 2. And we have the cube root of f plus 1. The way we get rid of a cube root is to cube both sides. So I go and drop parentheses before I do anything, and I cube this side. The cube kills the cube root, so what I have is f plus 1 equals -x plus 2 cubed. There's no reason to try to FOIL that or distribute that out. Doesn't make any sense to do that. It's just going to complicate things, so we're going to simply come in and subtract 1. So what we learn is f of -1, the inverse, is equal to parentheses x plus 2 cubed minus 1. If we were to graph this, we should see the inverse of those ordered pairs that we showed at the beginning, because that's what inverse functions do. If you wonder why I'm restating this so much, it's because if you know this one skill, on most multiple choice tests, you'll be able to recognize inverse functions. Here's another skill that we can use, and we can, again, get around this if we graph these and see if their tables are inverse. But another way we can do this is to create a composition like we did a couple of days ago. And if the composition ends up being x equals x, then the two functions are inverses of each other. So what we're going to do is do f of g of x. So the f of x function, in this case, actually, yeah, that's what we're going to want to do. Nope, I changed my mind. We can do either one. So I'm not going to do f of g of x. I'm going to do g of f of x. Because what I noticed is on g of x, I'll distribute 4. On f of x, I distribute 1/4. I don't really want to deal with a 1/4, so I'm not going to. So I'm going to rewrite my g of x function, which is 4 times x, but I'm not going to put in x. I'm going to put a big parentheses, minus 7. In place of the x, we are going to put in the entire f of x function. So when we do this, we have a distribution. 1/4 times 4 is x, and then 4 times 7 is 28. We carry down the 7, and we can see that this did not equal x, it equaled x plus 21, which means these two functions are not inverse of one another. But again, if you would have looked at their tables, you would have looked for integer ones and made sure that those values did actually have inverse. Now let's take a look at the next one. We can do either f of g of x or g of f of x. They're both the same thing. If they're inverse functions, it'll come out to equal to x. But if we think about this, what do we want to do? Do we want to throw a binomial inside of here, or do we want to cube a already cube root function? We definitely want to cube an already cube root function, so we are going to do g of f of x again. So I'm going to write the g of x function, but I'm not going to use an x. I'm going to be using a big parentheses in place of the normal x. And in place of that, I'm going to put in the entire f of x function, which is the cube root of x minus 1. Well, when we cube a cube root, they cancel, and that becomes x minus 1. We still have the plus 1 on the outside, so now we have like terms. Minus 1 plus 1 cancels each other out, so what we get is this function equal to x. When it equals x, that means those two functions are inverse of one another. So if you get anything other than x, like on part A, they are not inverse functions. If you get equal to x, then you have inverse functions. But once again, you could compare tables and make this same distinction. All right, so as we take a look at this one, it says a manufacturer of a gift box designs a box with lengths and widths, each, keyword there, each twice as long as the height. Find a formula that gives the height of the box in terms of the volume. Well, let's establish this first of all. Volume is equal to length times width times height. That's the formula we're going to develop first of all. Well, it tells us that the length and the width are obviously equal to each other because it says they're both are each twice as long. And we also know this, whatever the height is, the length is twice that. So the length is going to be equal to 2 h's. So let's go back to our volume formula. The volume is equal to the length and the height. Well, we're going to replace the length with a 2h. And we're going to replace the width with a 2h. Let's think about why that is. Reason why is because the width is equal to the length and the length is equal to 2h. So we substitute both of these in. The reason why we would do this is because we want to have a function with one variable. So little note to ourselves, length is equal to 2h, width is equal to 2h, and then the last thing was the h, so we have h here. So in this particular formula, the volume is equal to 2 times 2 is 4, h times h times h is h cubed. So the volume of this thing is equal to 4h cubed. Now the first thing it asks us to do is to give a formula that gives h as a in terms of the volume. Well, this is the volume in terms of the h. So what they're asking me to do here is to find the inverse. And I'm going to solve for the other letter. So we don't need to switch the v and the h because these are not generic like the other ones. We're just going to simply solve here. So we will divide by 4. So it will be the volume divided by 4 equals h cubed. And the way we get rid of a cube is with a cube root. So what we've learned is solved in terms of h. Well, h equals whatever the volume is divided by 4, and then we take the cube root of that value. So the next part tells us what the volume is. So what we have to do is take our volume, substitute in 640 because that's what they told us. So we have 640. We're going to take the cube root of that amount, and then we will have our height. Well, 640 divided by 4 is 160. And the cube root of that is a decimal, approximately 5.42. Now, this is one of those where we're in a little bit of trouble if we don't read. I did a lot of work, I did a lot of good work, but I haven't answered the question yet. The question says, then give the length of the box. I've given you the height of the box. Remember, it told you that the length is twice as much as the height. So we go back to this formula, and it's 2 times the height, which is 5.42. And we will get our length, and our length ends up being 10.86 with the rounding. I went back to my equation. Actually, we'll just do it. We'll do it based on our rounding. 4. We'll go 4. So that's what we would have there.